Today we're going to take a look at section 2.3, and we are looking at operations. The operation that we have seen so far is complement, right? It's saying everything outside the circle that's inside the rectangle universal set. That was complement. That was our first operation. The next operation we're going to take a look at is called set intersection. And the intersection of two sets is the set where they have the things that are in common. So from a picture point of view, this is a rectangle with two circles that overlap. That's the picture that you're thinking of. And the intersection is this part that they share. And it's exactly what you would mean when you're talking about street intersections, right? It's the part where they cross. The notation for this looks like an upside down U. Kind of looks like a script, like an N, like a lowercase n without the stick on the side. And this is defined to be the set of all x such that x is in A and x is in B. Has to be a member of both sets. Okay, a union isn't just where they overlap, it's where they overlap and everything else. You get it all. So, if we're looking at this same sort of a picture, the union is all of it that's inside either circle or both circles. It actually looks like a U when you join them together. It is defined to be x, such that x is in A or x is in B. And the or isn't an exclusive or. It doesn't mean it can't be in both. It certainly can be in both, and that's okay. But it's one or the other or both. So I liken the union to when you talk about somebody getting married, right? You get all of my debt and I get all of yours. Yeah, that's the way that works. Okay, you get it all. It's a merging of two completely different things all into one household. That's a union. There's one more. The one more is called a relative difference. The relative difference is the set of all elements in one set that are not in the other. It's similar to a complement, but it's in relation to two sets and not to the universal set. So if I have the, I'll use A and B here. I didn't write my A's and B's on the last slide. Sorry about that. It's the piece where they don't overlap. So it's the part that's in sort of A only, instead of A and B, or A or B. It's the A only part. And if we were to look at this one and we were to say A minus B, this is the set of all items x such that x is in A and x is not in B. Not in the overlap. Okay, and so we're going to do an example number one, that compares these ideas in terms of some elements, and the elements we're going to do it with are family members. So consider Mary, single mom to one child, Mark, Joe, single dad to two children, Jack and Jill, and Mary and Joe get married. Together they have two children, Ann and Andy. If M is Mary's kids, J is Joe's kids, find and describe the following. So what does M intersect J mean? Kids they have together, the kids they share. So I'm going to say kids in common. And just for the sake of making it simple for ourselves, we'll talk about as though biology is involved here, right? Like biologically, they're children. That's what we're talking about. We all recognize that they're all children. We get that. I get that more than anybody. I got those kids, right? That's not what we're talking about. We're just talking about biology for the moment. So, who is that? That is Anne and Andy. Okay, so what is the union? What does that mean?
All the kids.
It means all the kids. Right? This is Thanksgiving dinner or whatever it looks like when everybody's in the house. So who would that be in this case? Mark, Jack, Jill, Anne, and Andy. I think I got Jill. Mark, Jack, Jill, and Andy. I think I got them all. Yeah, we're not talking about everybody in the household with the parents, just talking about the kids. Yeah, just kids. So what would M minus J, that minus means relative difference here. What is the relative difference of M and J? Mary's kids.
So would it just be Mark?
Yes. So these are, how did I write it down? That's how I wrote it down. The ones that are Mary's only, right? The ones she entered the marriage with, so to speak, in this case, and that is, in fact, just Mark.
Is it ever going to ask for both, like M minus J and J minus M?
It could, and of course they'd be different, wouldn't they?
Yeah.
So M minus J and J minus M are actually not going to be a commutative relationship, right? Commutative means you get the same quantity when you're done. It's not going to work. You will explore what happens when you do unions and intersections if those are relationships that are commutative or not. And I can't remember if we do it in our notes or if we do it in our, we do it next. Here I am. Probably put that there on purpose. Yeah. So on this one, when we're looking at the commutativity of set intersection and set unions. So if we're looking at all sets, so this upside down A means for all sets A and B. The intersection of the sets doesn't matter whether you're talking about A intersect B or B intersect A. They're the same. And if you think about the picture, right? One more back. It should seem very clear. Right? It's the same overlapping piece, no matter what order I think about it in. While I've got my picture up, what do you think is going to happen for my union picture down here?
It'll be the same as well.
Yeah, it's also commutative. So if I'm doing the union, same thing's happening. But you'll notice that I'm not going to write the relative difference in here because it would, in fact, be different. In terms of my picture over here, the blue part is A minus B, and if I wanted B minus A, it'd be this red part, right? Yeah. So those are not going to actually be the same. They will not go in this blank. The next one is called the associativity. The associativity of the set intersection and union. So in order to talk about associative properties, we have to talk about having three sets. So this is for all sets A, B, and C. If you have A intersect B intersect C, it's the same thing as having A intersect B intersect C. Intersection, same thing. Doesn't matter what order you put it in or how the grouping is in this case. You're going to get the same part of the picture. And you might be thinking, well, but we only did a picture. I only did a picture a minute ago with two sets. What does it look like for three sets? We'll draw more about them later, but just because I'm thinking of it now, it looks like this. So it starts to look a little bit like Olympic rings, right? And if you're looking at the intersection of all three, it's this piece in the middle, right? That's where they would all three intersect. And if you do the union, you're going to have the same thing. So if I do A union B union C, I could do A union B union C. And picture-wise, I would have this same thing, except it would be everything I'm highlighting right now in yellow, which is everything in any, I should say, of the three circles. That would be my union. I get all the stuff, all the categories. And there is a distribution property as well. So if you flip your page, we still need 3 sets. So for all sets A, B, C, if you have A intersect B union C, it's a terrible U. That's better. This is the same as A intersect B union A intersect C. Okay, so you have that distribution property like we have with addition and subtraction, and this is the way it works for sets. Okay, so a couple of more definitional kinds of things. They're not necessarily related to this, but we're going to be using them very shortly, so they're kind of grouped in here at the moment. The cardinal number formula is a very interesting one. It tells us how we can count how many things are in a set. It says that if I'm looking for the number of items in a union, I could add the number of items in set A plus the number of items in set B. And in fact, I need to subtract off the number of items. So the number of items in their intersection. There we go. And in some ways, usually students look at that and say, well, shouldn't I add them? And that's a really good question. So I'd like to show you what happens when we actually do this with 2 sets and why it's subtraction. So here's set A and here's set B. If I were to include all of the items that are in set A, I would include everything in circle A. Everybody good with that? And then if I were to go back and I were to include, add on all of the items that are in set B, I would include all of these. And what happened when I did that? I double shaded the intersection, right? That's why I'm subtracting it off at the end, is because I counted it twice. Right? I counted it when I colored it in yellow, and I counted it when I colored it in green. So I've counted it twice. I have to remove it one of the times to remove my double counts. So that's where that's coming from. And the last set operation that I'm going to define for you, which we won't use extensively, but we will see it come back up when we talk about addition and subtraction. I think that's right. Yeah, it's with addition and subtraction. It's the Cartesian product. So the Cartesian product is the set of all ordered pairs such that the first component comes from the first set and the second component comes from the second set. And I'm going to give you an example so you can see what it's referring to. We're going to take set X to be the numbers, or the letters, in fact, X, Y, Z. And the set, I think I said the set X, I meant the set A. Sorry, the set B then, we're going to let be the numbers 1 and 2. Leave just a little space underneath those, and then come down here and you're going to write down a multiplication kind of symbol, and then B like that. So the Cartesian product is going to be a collection of ordered pairs where the first element comes from the first set and the second element comes from the second set. So the ordered pair X1 would be one of the elements in the Cartesian product. Another of them would be X2. What else would I have in my Cartesian product? Y1 and Y2. And what are my last ones? Z1 and Z2. Okay, so that's what they are. They're a collection of ordered pairs. It is interesting to note that there's actually an equation present here. I'll change my color just to identify that we're finding something different. What I'd like to do is to just count how many things there are. So how many items are there? What's the cardinality of set A? 3. What is the cardinality of set B?
2.
It's 2. And what is the cardinality of the Cartesian product? It's 6. Does everybody see where those 3 numbers came from? Just counting the pieces there. Do you see any relationship between 2, 3, and 6 that you're very familiar with? Of course you do. 2 times 3 is 6, right? And that's actually always going to be true. The number of items in set A times the number of items in set B will be the number of items in the Cartesian product. Okay? Now, those aren't the things that are in them. It's just counting how many of them there are. Okay? Just a counting argument there. Okay, so we are going to look at some Venn diagram stuff. We probably will get done with A and B. That's where I usually get to. So let's take a look at how we think about and use Venn diagrams to find intersections and unions with complements and relative differences and all the like. So question number 2, or example 2, says that we're going to use a Venn diagram to shade the following sets. So the first thing you're going to do is you're going to draw a rectangle, and then you need circles representing however many sets you have. Here I have only 2 sets, so I only need 2 overlapping circles. Our next example will have 3. And you're going to label them as A and B, since that's what they're labeled, and we always have the universal set out here, U. One mistake that students like to make is not drawing a rectangle on the outside. You need that there, okay? One of the reasons you'll need that there is because you need to recognize that there are things that are not in sets A and B. And that rectangle actually gives some sort of a defining remembrance for us that we've got this sort of space on the outside of the circles that exists, okay? Now, in order to do what I'm doing on this problem, you could do this problem differently and it would work pretty well. But I want to show you a very structured way to approach this problem, because once we get to 3 circles overlapping and the problems get more complicated, it becomes very, very difficult to sort of reason your way through what should I shade. We could probably reason our way through what should I shade on this problem because there's only 2 circles. Okay, so bear with me, even if you think this is not necessary, it becomes more necessary the more complicated it gets. So what we're going to do is we're going to label the regions, the areas of my picture, with numbers. Okay, I usually label 1, 2, 3 across the middle of my circles and a 4 outside. These are just labels. If you wanted, you could use, letters, X, Y, Z, and U. It wouldn't hurt anything. In fact, your book uses letters at some points. I just use numbers. There's no real reason why. I just do. Okay? They're labels only. They're not items that are there, just labels. And what you do is you look at what they're actually describing in your problem. They are describing A complement and B complement. So what we're going to do is we're going to write down with the pictures labels that we created what numbers are the regions that are for A complement. So looking at my picture, what numbers are in the A complement region?
1 and 2.
Those are in the A region. We want A complement. So 3 and 4. Okay, so complement means everything not in A. That would be 3 and 4. 3 and 4 are not in A. And we're going to do the same thing because they also have B complement listed there. B complement, everything not in B. 1 and 4, 2's in B, 2's in B. Okay? Got to look back at the picture. It's okay. Is everybody good so far? We know where the 1, 2, or 1, 3, and 4s have all come from at this point. Fantastic. Kind of like when you're doing old-fashioned addition, like first grade stuff, you write this plus that, you write it vertically, and then we write the result underneath. Same idea, I'm drawing a line to do the result underneath. And I want to join A complement and B complement with whatever symbol that is in my problem. And that here is a union, right? So, what does union mean? You get all of it together. So, don't look at your diagram. That's not helpful. Look at the numbers. That's why you did it. We're going to include every number that I already wrote down. So we're going to include the numbers 1, 3, and 4. That's the union. Common mistake number 2 is stopping right here. You did all the hard work and you just don't answer the question. Because the directions actually told you to do what? Shade. So go back with whatever shading utensil you'd like. If you want to use colors, then that's fabulous. If you just want to use your pencil, no problem. We're going to shade regions 1, 3, and 4. Okay? We're going to try one with 3 circles before we quit today. There are 3 circles here, but I have nicely enough not given you any complements to deal with on this problem. So 3 circles always overlap as such. Universal set. Again, I usually label top to bottom, left to right, so A, B, C, like this. If you label differently, it doesn't hurt anything. You're just going to create more work for me. Don't do that. That's not very kind, okay? It's just not. Okay, got to label the regions with the numbers, right? Give them labels. So we're going to go across the top, 1, 2, 3. Across the middle, 4, 5, 6. The C part at the bottom is 7, and then there's a number here on the outside, 8. And hopefully you recognize what I was meaning before about it getting complicated. I've got 8 regions now, not 4 regions to figure out. That's a lot. We're not going to get any bigger than 3. Okay, yeah. Okay, parentheses means start here first. That's not really what they mean, but you know what I'm saying, right? They tell you that's where you start. So we're going to work inside our parentheses. The goal is not to simply write down all the sets and all the numbers. It's to write down only what we need. It says I need set A and set B. So I need to look at every number that is actually in set A. So what numbers are in set A? 1, 2, 4, and 5. In whatever order you like. It doesn't matter. It'll be just fine. What numbers are actually in set B? 2, 3, 5, and 6. And because these have a parenthesis and they're grouped together, I need to sort of do this pause and relate them with what operation? What does it say? Intersection. So, again, the goal is to use what I just did. I want to use those numbers, and I need to do the intersection. What does the intersection mean?
Numbers that they have in common.
Numbers that they have in common. So which numbers do they have in common?
2 and 5.
2 and 5. So we're going to write those down. We're almost done. We did everything inside of parentheses. Moving to the outside of the parentheses, I have set C. What numbers are in set C? 4, 5, 6, 7. And how am I told to relate A intersect B with C? Union. So again, use the work you just did. Don't recreate the wheel by looking at your picture. It's not going to be real helpful. Looking at what I just did, if I want the union, what does that mean? All of them. Every number that's sort of parenthesis outed, the bracketed, whatever, in blue, it's all of those. So I have 2, 4, 5, 6, 7. Everything from that blue bracketed set. Yes, Colton?
And since the 2 and the 5 are kind of like a different operation, would you shade it like a different color first and then shade?
We're just shading, we only shade the result. It doesn't matter. They're still equally valid.
Okay.
Yeah. So again, though, we do need to shade. So I need to shade regions 2, 4, 5, 6, and 7. So here's 2, 4, 5, 6, 7, and I'm done.